Hello guys, we are starting with chemistry today. So in the IB, we have structure 1.1.1. The name is Introduction to the Particulate Nature of Matter. But before starting the topic, I want to talk a little bit about me. So first, I'm currently full-time chemistry teacher in an international school. I am IB chemistry examiner with more than 8 years of experience. The last exam that I graded was the paper 1B. It was in May 2025. I have also marked paper 2, paper 3, internal assessment, and extended essay. I have 10 plus years of experience as a chemistry teacher and 8 plus years of experience in the teaching the program, the IP program. In total, I could say that I have more than 20 years of experience as a chemistry teacher, experience as a private tutor, and also I am been teaching online for more than 5 years. Okay, so now let's start it. Okay, the structure of the video. First, I will talk about the learning objective. So the learning objective created by the IB and the shared in the syllabus. Then I will explain the topic carefully using different resources. And more importantly, we will practicing past papers questions and also question provided by different resources like the IB Pearson, IB Oxford, and I am also refining some topics using Cambridge, Brown, and Sundal, which are college books. Let's start it. So the topic is Structure 1.1.1, Introduction to the Particulate Nature of Matter. I want to show you the learning objective as is in the syllabus. So it says that elements are primary constituents of matter which cannot be chemically broken down into simpler substances. Then we have that compounds consist of atoms of different elements chemically bonded together in a fixed ratio. And then we have that mixtures contain more than one element or compounds in not fixed ratio. So those are the learning objectives for this particular topic. So I will explain you in detail. So first, we could say that matter is divided into two main blocks. So the first one, we have the pure substances, and pure substances are also divided in two, which are the elements and compounds. And then we have the mixtures. So these mixtures are also divided in heterogeneous and homogeneous mixtures. So as you know, pure substances and elements are the ones that we can find in the periodic table of elements. So we have sodium, we have hydrogen, we have potassium, we have chromium, we have iron. All the elements that we find in the periodic table, they are elements and they are pure substances. Okay, they are pure. And also we have that compounds and another kind of pure substance. So compound substances that contain different elements. For example, I have water, H2O. This is a compound, as you know. We have the element of hydrogen, the element of oxygen. We have H2SO4, which is sulfuric acid. We have three different kind of elements. They are a compound, and for that reason, they are also considered pure substances. As another example, let's see potassium nitrate. This is another compounds because they have different elements in the same substance and also are classified as pure substances. On the other hand, we have mixtures. Mixtures can be divided in two, homogeneous and heterogeneous mixtures. So I will talk about in depth and how can we differentiate homogeneous and heterogeneous and what are the main features for this. This is the most basic thing ever in chemistry. So here we have this table with the name of some elements and symbols. Um, have only one letter as carbon here. Carbon is C, fluorine is F, potassium is K, but here we have an element with two letters. Always there is a capital letter followed by a normal letter over here. Here we have again the same example, but the first one is always capital, and then we have the lowercase, and here we have only one letter. As I mentioned, we are explaining at the beginning, okay? This is very easy. Now, some elements are found in native form. Here we have the example of nitrogen. This is widely used element used in refrigeration. So here we have an example. If you go to the kitchen and you have in the behind part of the freezer, and in the fridge, you will have some tubes, and those tubes are the ones that contain the nitrogen, okay? Or this is what I remember from the fridges that we have. So here we have gold. Gold can be also found in native state. Okay, so here we have one miner that found a piece of gold by mining. So this is one of the kind of mining that is made by hand. So only by moving this ball, they can get a rock of gold. And this is one of the ways to find the native form. So, and this is two examples, the two main examples of nitrogen and gold. Here we have some elements are found in chemical compounds. So some elements are found native and some elements are found in chemical compounds. For example, iron. Here we have iron SO4. So this is how we can find the mineral. This is how we can find the rock in nature. After a process, a chemical and physical process, then we can have the pure iron, okay? But this iron was found in a chemical compound. This is one of the examples. The chemical formula of a compound uses a combination of chemical symbols of its constituent elements. I am highlighting these ideas because those are the main ideas that the IB is expecting for you to know, okay? So chemical formula, here we have an example of chemical formula. Let's say sulfuric acid. I am using this substance as an example most all the times. So here we have 4 atoms of oxygen, 1 atom of sulfur, and 2 atoms of hydrogen. Okay, so this is compound uses a combination of chemical symbols. Here we have the 3 chemical symbols. The subscript here is used to show the number of atoms of each element in a unit of the compound. As I mentioned before, this will be our subscript. If there is no any subscript, for example in sulfur, it means that there is only 1 atom of sulfur. So for this chemical compound, we say there is hydrogen, we have 2 atoms of hydrogen, sulfur, we have 1 atom of sulfur, and oxygen, we have 4 atoms of oxygen. So here we will talk about mixture and features, the main features of different mixtures. Okay, so here we have that mixtures are everywhere. So unlike pure substances, mixture can vary endlessly in composition, like the ingredients of milkshake or maybe different kind of foods. You can find different kind of mixtures everywhere. Okay, so air is a mixture. So you know that air contains different gases. Okay, so nitrogen, oxygens are the ones that are in more percentage in air, but air is made by different gases. Okay, so they are a mixture because these gases are not chemically bonded. So oxygen is not bonded to nitrogen. Oxygen is by itself and nitrogen is by itself, but they together create this mixture of air. Okay, and there are many other gases. And I want to explain this as well. In a mixture, all the elements keep their original properties. Okay, as I mentioned, in oxygen, in air, oxygen has its own properties, nitrogen has its own properties, hydrogen has its own properties. They will have their original properties. Here we have mixtures versus compounds. So mixtures have not fixed composition. Okay, so remember that in compounds we mentioned before H2SO4. This is 4 atoms of oxygen, 1 of sulfur, and 2 of hydrogen. In a mixture, this is not always the case. The proportions can change. And here we have homogeneous and heterogeneous mixtures. Homogeneous mixtures have an uniform composition. Okay, for example, the salt water, bronze, particles interaction between components are similar. So these are the homogeneous mixtures. So when you can see a glass of juice, here we have a glass of orange juice, you can see only one component, the orange juice, okay? But here we can have a mixture of the fruit and water, and this is an homogeneous mixture. There is only one phase, one element. If you look at it, it looks like it's only one. This is the main feature of an homogeneous mixture. When we have heterogeneous mixtures is when you have different phases, when you can see different parts. Let's say, and this is something that we use in teaching 6th or 7th grade when we have pizza. We can see that we have the pepperoni, we have the cheese, different compounds. Yes, you can see different pieces, different parts, different colors, different textures. This is an heterogeneous mixture. Okay, so here we have example of mixtures. So air, as I mentioned before, a component one is nitrogen, the component two is oxygen. The particle interaction, the dispersion forces. So there is a kind of interaction between these particles. And the interaction of the mixture is dispersion forces. Okay. Bronze. Remember that this is an alloy. So bronze is an alloy made of these two elements, copper and zinc. You can see only one phase. It's only one metal, the one that you will see. That's why in the particle interaction, we talked about metallic bonding when it comes to zinc and copper. The metallic bonding will be the interaction of the mixture. We have positive ions, and these positive ions are glued by electrons. And this is when we talked about metallic bond. So in this mixture in particular, in bronze, one of the atoms is copper and the other atom is tin. Another example here, we have salt water, sodium chloride. This is the first component. And then we have water. And sodium chloride is salty water. It's an ionic bond. And then the interaction between molecule of water and molecule of water, hydrogen bonding, and this will be the hydrogen bonding. The interaction will be on dipole afterwards, okay, more in depth. Those are the examples of different mixtures. Another very important part of this topic is the changes of a state of matter. Then we will talk about the separation of mixtures. So in this picture, you can see the different states of matter. We have a gas, here we have the gas, here we have the liquid, and here we have the solid, something that I will explain in detail in the kinetic theory, how these particles are arranged in different states. Here we have deposition and sublimation. These two are tricky. Why are tricky? Because there is no a liquid state as an intermediate. So from solid is changing to gas, and from gas is changing to solid. Those are the ones that you have to memorize. So deposition is when the gas becomes a solid, and sublimation is when the solid goes to gas immediately without the liquid state. Example of this one I will show you later, but I will put iodine. This is one of the elements. Here we have CO2 in solid state. This is another example of the sublimation. It looks like a cube of ice. Maybe you have used this before in an experiment. I think that you use in the experiments in cooking in some restaurants when they are showing a cloud, a gas release from the food, is because they are using CO2, this dry ice, another name that they buy. This is a sublimation. Here we have evaporation, and then we have condensation. Evaporation is when the liquid passes through overcoming the atmospheric pressure, so the molecules a higher pressure than the atmospheric pressure, and that's why the particles jump liquid to gas. Condensation is when the gas becomes a liquid. And here we have the easiest one, freezing and melting. So melting is when we have our solid, we submit the solid at high temperatures, and then we have the liquid. And when we put the liquid water in our fridge, then we have a beautiful ice cube. As I mentioned, guys, we are starting from scratch. Most likely you know this already. You need to still pay attention to this composition and so. Okay, guys, now that we know the main difference between homogeneous and heterogeneous mixtures, now it comes the topic to separation of mixtures. So depending on the mixtures and depending on the compounds that I want to get from that mixture, I need to use a different separation technique, okay? The filtration process. In this filtration process, let's say that we have a mixture, okay? Let's use a mixture of an insoluble solid and liquid. Let's say sand and water. This is our mixture. What are the instruments that we have, or the glass material that we have in these methods? Here we have a beaker, then we have a funnel, then we have a filter paper inside the funnel, then we have a conical flask. Okay, these are all materials. How is that? So you have the mixture of sand and water. You pour the mixture through the funnel and the filter paper. So the filter paper will trap the solids that are not soluble in water, some rocks, silicon oxide, sand. They will be trapped in the filter paper inside the funnel, and what we have here will be the water. Maybe water in this case is not totally pure. We cannot say that we are separating completely water from sand, but definitely we are getting the separation of water and and sand in some extent. Okay, here we have important vocab. The residue, this is the substance that is inside the filter paper, inside the funnel. Okay, then we have the filtrate, which is the clear substance after this filtration process. Remember that also we have this glass rod. We use it to make the mixture in the funnel. Okay, and this is how we separate a simple but important filtration process. Some words that we need to keep in mind: filtration, so it's the method itself, the one that I showed you, about how a substance is solved, is soluble in another substance. The residue is the one that is in the funnel at the end of the separation mixture. Filtrate will be the clear substance here, and crystallization will be another process in order to get the clearer and purer substance. Okay, so this will be our filtration. Okay, now this is our distillation process. So first we need to know that this distillation process is mainly used to separate a mixture made of two substances in a liquid state, and they are miscible. So one of the substance is soluble in the other one. For example, let's say water and ethanol. As you know, alcohols, and this is a very short-chained alcohol, will be soluble in water. I'm not saying that all alcohols are soluble in water, but this particular is soluble in water. This process is used to separate these two liquid substances. So I want to separate water from the ethanol. Okay, and remember they are miscible. So this is what we need to separate using this method. I want to talk about this setup material, and here we have the distilling flask. Here we have the connection between a condenser and the distilling flask. Here we have the thermometer, which is the one that is showing me the temperature of the substance that I want to separate. Here we have the condenser. This is the main character here. Here we have a connection between the conical flask. We have our conical flask. Remember that all of these need to be attached to universal stand here and a universal stand here. Sometimes we have another universal stand here to support the condenser. Okay, how does all of this work? So here we have the substance, and we talk that this is a water and ethanol mixture, right? Here we have our mixture. We are heating up the mixture, okay? One of the two substances we have a lower boiling point. In this case, ethanol will have a lower boiling point. This temperature is the one that I will check in my thermometer. So depending on the altitude, the boiling point of the alcohol will change. But this is something that we can check in different booklets. This thermometer is the one that is telling me what is the temperature of the substance that I want to separate. Generally, the solvent is the one that has the lower temperature. In that case, ethanol. Now we get to the boiling point of the ethanol. This ethanol is changing from liquid state to a gas state. If you see here, we have the bubbles of the gas, and let's change the color. This will be the gas produced. Okay, this is the temperature of the boiling point of the ethanol. In this case, the particles have a lot of energy, but now are touching this condenser. What is this condenser? As water in. So imagine that this is a hose connected to the tap water in the laboratory. Okay, it means that this water is fresh water, and this water is circulating over here, the cold water. That's why if you have the gas and this gas is making contact with a colored surface, the gas becomes a liquid again. So the gas becomes a liquid as is a colored surface. It has all of this surface area to become a liquid. What happened to the energy of the gas? There is a hose connected, and we are throwing this in the sink. okay, in the laboratory. That will be the hot water. So remember that the hot particles here in gas state are making contact with the color surface. So the water that was in the cold water now will be hot because it's absorbing all the energy from the gas. We are getting rid of this hot water in the sink. What happened here? All the liquid is finally distilled. And here we have the liquid. If we talked about a mixture of water and ethanol, here we have the ethanol and here we have the water. And this is how the method is useful to separate one homogeneous mixture of two liquids. Okay? The solvent has a lower boiling point. The gas is collected here and then the gas is condensed here in the condenser. This is the distillation process. Guys, this is another method to separate mixture. And even though this is not widely used to separate mixtures, this is one of the methods that is used to determine how many substances sample has. In this case, we are using the chromatography of the mobile phase, stationary phase. So it will have two phases. This is the simple chromatography and this is the one that IB is expected for you to know. Okay? So as you see, here we have paper, here we have a petri dish, here we have a line made by you using a pencil because it's graphite and it won't be displaced by water. First we have some inks. In this example we have red ink, then we have a green, then we have purple, and then we have a black. And the idea is that we are separating every ink in their different components, or we want to see the different components. Depending on of the nature of the substance that I want to separate here, I want to use a determined solvent. Okay, sometimes the ink is soluble in water. I will use water because water will move, will displace it. Sometimes I can use ether or I can use another solvent to move it. When we talked about mobile phase, we are talking about the water because the water is the one that will be mobile. For the capillarity of the paper, of the cellulose, it's absorbing the paper, water is going up. Here, this is moving the different parts of the components of the ink, and that's why we have different colors, you see? So we are starting here, this is in 0 seconds, 30 seconds pass through, then we have a different phases, and this will be our result. This is how it looks, the chromatography. Small sample spots are placed on chromatography paper. As I mentioned before, the paper is saturated with solvent to allow movement. The components separate based on their affinity to the solvent. This is used to identify pigments in substances like food coloring. Here we have a very important factor, and this is the retention factor. We need to measure the distance traveled by the solute, traveled by the solvent. So in that case, this will be the distance traveled by the solute. If you see the red color, that will be the distance between the line and the distance by the solvent. In that case will be the water, the distance required with water. If you see, we can calculate this RF distance traveled by the solvent. So depending on this R, we will see what is the relationship between the solvent and the solute and the solvent. Here, a retention factor value suggests the substance interacts less with the stationary phase and more with the mobile phase. Will interact more with water than paper, while a lower retention factor value indicates the opposite. So this is the indication of the retention value. Here, retention factor, the more interaction with water, talking about the solubility of water. Here we have the RF for A. So here we have A and here we have the distance. You see 0.15. Here we have B, in that case is 0.87, and here we have C, which is 0.38. If you see, this is the sample. The sample is the one that contains the three colors. And this is how we can differentiate the three different colors on pigment from that mixture. What could we say about these results? We could say from A interacts less with the mobile phase and more with the stationary phase. The higher here B is the one that interact more with the mobile phase, which is water. The higher the retention factor, and you can see the symbol here, the more interacting with the water. interact the most. Sometimes, and some teachers are relating this with solubility, but we could say that this is a mistake to talk about solubility of water and the Big Bang at the same time. This is our chromatography. Okay, guys, now we have the questions. So these are past paper questions, are strictly related to this topic that we studied today. That's why I am not putting a lot of questions, but the ones that we have only about this insulated structure 1.1.1. Okay. So the first question is this one: which of the following are homogeneous mixtures? Take your time and then you continue with the video. So I will approach this. So we have an aqueous solution of sodium chloride. Okay, sodium chloride dissolved completely. So this is an homogeneous mixture of pentane and hexane. Well, what is key here is that pentane is a nonpolar substance and hexane is a nonpolar substance. It means that they are miscible. One is soluble in the other one, meaning that when they are mixed, we can see only one phase. So that would be an homogeneous mixture, and a mixture of ethanol and water. We could also see only one phase, meaning that it's an homogeneous mixture, and the answer is D. Second question, guys, you can stop and then give play to see the answer. Which diagram represents an heterogeneous mixture? So heterogeneous mixture, remember that is the one that we have different components. Okay, so we have different. So if you see this could be an heterogeneous mixture because we can see two phases, two different parts. This could be an heterogeneous as we can see two components. Definitely not, it's only one component. So could say that this is an homogeneous since all of the parts are exactly the same. It's the same component. We can exclude this one. Now, considering this one and this one, we can pick only one, or we could homogeneously distributed in the area. They are completely separated. I will go for this one because they are completely separated and we can distinguish two compounds. Here we have the correct answer. This is the heterogeneous mixture. They are very separated. Here we have another question. Please stop the video, try by yourself, and then continue. Which statement describes all homogeneous mixtures? So any sample has the same ratio of the components. Okay, let's put it aside. This could be the components are covalently bonded. No, components are not covalently bonded. In that case, that will be a chemical interaction, and in mixtures we don't have chemical interactions. The components cannot be easily separated. This is false because we have many separation methods that can be separated different, no matter if it's homogeneous or heterogeneous. The mixture needs a specific ratio or components to form. This is not true. For example, you can have three bananas in water, three pieces of banana in water, or two pieces of banana in water, and it will be still an heterogeneous mixture. Yeah, or homogeneous mixture. The mixture needs a specific ratio of the components. No, it doesn't need a specific. If you have, for example, 20 milliliters of ethanol in 50 milliliters of water, or you have 10 milliliters of ethanol in I don't know, in let's say 125 milliliters of water. Okay, this case is the same proportion. Let's say you have ethanol, let's say 20 milliliters, and water, you have 100 milliliters. That will be homogeneous. If you have 10 milliliters and you have 100 milliliters, this will be also heterogeneous mixture. It won't affect. So the right answer is A. An example, the same ratio of the components. The thing is that here we have sample. Remember that sample is when you have the mixture and you take one of them. So if the ratio here is 10 is if the ratio here is 9 to 1 and you take one sample, the sample will have the same ratio, 1 to 9. Yeah. So if this is 30% salt and water and you take only one small part, that will be the same 30%. Is the concentration won't change. Okay, so that's why A is the correct answer. Here we have which statement describes all homogeneous mixtures. Okay, this is the one that we saw. Here, which is correct? continue when you finished? No, because there is no chemical interaction. There is not an average of chemical properties, since they will have their own properties. The components of a mixture, they will have their own properties. Mixture and heterogeneous? Of course, we have mixtures that are homogeneous and heterogeneous. Are average of the properties are an average of the individual components. This is not true at all, because there is not an average. There is not chemical interaction between one compound and another compound. This is the correct answer. And the components retain their individual chemical properties. That's good. That's why we can separate them. And let's read the last one. So that's not true, because of course we have homogeneous mixtures as well. Yes. So guys, here we have some questions from the book. I want you to give them a try. I will leave them here. You can stop, you can solve them. I will show you the mark scheme in a moment. This is 3, 4, and 5. The idea is that you try, and once you solve them, you check if your answer is correct. And here we have 5 and 6. All of these questions are taken from an IB book. So this is what is expected for you to know. Okay. Once you finish these questions from 1 to 6, then you can see the answers. Here we have the answers for all of those questions. As the questions are taken from the International Bachelor Organization, and these particular questions, the last one, the IB chemistry book for Pearson. Okay, guys, this is everything. I think that if you are able to solve all of these questions, the past paper questions, you are good to go regarding this topic. Okay, so see you in the next video.